Hello everyone, my name is Stefanos Voulgaris, and today I will present to you our latest research from the National Technical University of Athens, the School of Civil Engineering and Institute of Structural Analysis and Anti-Seismic Research. We propose a paper on smartphone-based photogrammetry for prosthetic design and topology optimization. The present work is an engineering framework developed within the ICONS2026 and Mediscope 2026 initiatives and funded by the European Union. This presentation describes a low-cost, accurate methodology based on consumer mobile hardware and generative design algorithms for patient-specific upper limb prostheses. Here I will explain our capture protocol, point-to-mesh reconstruction, finite element boundary conditions, and structural optimization results. Understanding the context of this study starts with the accessibility barriers of the global prosthetics market. Standard clinical workflows for custom personalized prosthetic socket manufacturing use manual plaster molding or sophisticated high-end laser 3D scanners. Plaster molding is laborious, uncomfortable for the patient, and dependent on operator skill. Conversely, optical laser scanners are prohibitively expensive, thousands of dollars, and require special operating software, which isolates the design pipeline to centralized, advanced urban medical facilities. This leaves amputees in remote or resource-constrained settings with little recourse to modern orthotic devices. This work presents a digital replacement for those old barriers. By replacing expensive proprietary hardware with standard consumer mobile device photogrammetry, we democratize the digital scan pipeline. This open software-driven workflow bypasses centralized infrastructure entirely and provides an accessible basis for decentralized, patient-specific orthotic generation directly at community-level clinics. The integrated 4-stage workflow, from physical anatomy to structurally optimized finished devices, is shown on the slide. The pipeline begins at step 1, the scan target, where we implement a systematic protocol for taking highly overlapping images of the patient's residual lower arm and a full lower arm with a standard mobile phone camera. In step 2, when reconstructing, these raw images are computed using cloud and alignment algorithms to produce dense point clouds and are converted to a perfectly scaled digital twin mesh. Moving to step 3, using Design CAD, this virtual mesh is the master reference for a computer-aided engineering suite, where we perform digital sculpting and Boolean operations to draw the socket constraints around the patient's anatomy. Finally, in step 4, the raw CAD model is optimized by iterative weight minimization finite element analysis to remove unneeded material weight while preserving absolute structural stiffness. Let us examine more how we perform each stage in the next slides. Step 1 focuses on our controlled capture protocol. As photogrammetry algorithms depend on locating consistent pixels across many images, the quality of our input photos affect the geometric accuracy of our output. 3 rules prevent visual artifacts, skin glare, or shadow movement. First, the operator performs a complete 360 orbit of the forearm, taking consecutive overlapping photos at uniform angular positions. The second strategy is the dual pitch and angle strategy, where we prevent geometric gaps in the final 3D mesh around difficult anatomical features like the elbow joint and muscular contours by changing the smartphone camera height during sequential orbits, alternating low and high camera elevations. We then address scale. Photogrammetry operates in a dimensionless pixel coordinate space. We place a flat 5 cm by 5 cm reference target next to the limb to establish absolute physical measurements. This fixed metric target enables our software to scale the digital workspace back to physical millimeters. Moving on to stage 2, a cloud stitching engine processes the image dataset for point-to-mesh generation. A computer analyzes pixel configurations across the overlapping photographs and tracks individual dermal features, freckles, and light variations to determine camera absolute spatial position for each frame. This stereophotogrammetry triangulation gives a dense spatial point cloud. Software applies surface triangulation algorithms to mathematically join these dense points to form structural triangular faces, encasing the continuous closed geometry of the arm. The final important step is scale correction. When locating the boundaries of the 5 cm target marker within the virtual space, the software determines the pixel to millimeter ratio and applies a linear scaling matrix to the model. Using this method, a very accurate digital twin is produced that matches the real arm dimensions of the patient within a millimeter margin of error. Once the generated mesh is scaled, we move on to stage 3. In CAD design, we do digital sculpting in parametric solid modeling software. The digital twin is our master anatomical reference. The initial phase of this design is setting the offset boundary. We isolate the residual limb and define a 2 mm gap tolerance along the inner walls. The clearance is 2 mm. This is critical. It provides the precise physical space to insert an elastomeric inner linear cushioning the skin and preventing localized friction. Next is the solidification. We project the outer boundaries outward with different thicknesses to form the default unoptimized solid mass of the socket shell. And finally, a fusion operation is performed, incorporating a standard wrist interface coupling mechanism and structurally fusing our custom sculpted socket base with a digital model of the full lower arm to obtain a continuous CAD assembly for engineering simulation. Before optimizing the prosthetic assembly, realistic operational forces under finite element boundary conditions are applied to the digital CAD model. Two particular loading cases mimic everyday user interactions. Axial compression is the first load case and represents a 150 Newton force pushing along the lengthwise of the prosthesis. This is like having a patient lean on something or push their body weight upward from a chair. A second load case evaluates tensile strength under a 100 Newton downward force to simulate pulling a dynamic gravitational load like a heavy bag. For material properties, the simulation assigns isotropic polylactic acid or PLA characteristics. We selected PLA because it is the most widely available, reliable, and easily manageable 3D printing polymer available today, which reflects our engineering assumptions and community-level fabrication realities. This brings us to our structural optimization framework, where we apply computational mechanics to refine our geometry. We employ the solid isotropic material with penalization, or SIMP algorithm. The mathematical goal of the SIMP method is to minimize global structural compliance under our active multi-load conditions, which is equivalent to maximizing the overall structural stiffness of the prosthesis. The algorithm evaluates the relative density of each individual finite element using the material interpolation equation shown on the slide. Here, epsilon is the penalized elasticity modulus of the element, rho represents the localized pseudo-density value between 0 and 1, epsilon 0 is the baseline modulus of the solid PLA, and P is the penalization power factor, set to 3. These penalization forces intermediate densities toward binary states, either 0, meaning a void of empty space, or 1, meaning fully dense solid material. Simultaneously, we enforce strict volume constraints to maximize efficiency and reduce user fatigue. The final structural volume fraction is restricted to 0.55, forcing a major 45% reduction in the total solid volume of the initial CAD cell. Crucially, the 2 mm inner socket interface and the wrist mechanical attachments are locked as non-design spaces, keeping them entirely solid while the algorithm is given the freedom to dissolve low-stress zones. The net result of this optimization is an organic, very complex web geometry orientated strictly along internal stress pathways. This methodology shows how we translate this complicated digital data to real-life clinical implementation. These generative optimized structures have large void spaces and are not suitable for subtractive manufacturing like CNC milling, but they are suited for additive manufacturing. Direct 3D printing enables us to manufacture these geometries without the tooling cost or production complexity. Physical benefit is great for amputees. The reduced mass decreases muscle fatigue in the upper arm and shoulder, leading to improved patient comfort and daily device compliance. With just a consumer mobile phone and a desktop 3D printer, this complete pipeline connects advanced structural engineering with localized rural clinical delivery systems. While the current methodology validates the mathematical and geometric foundation of this workflow, we identified 3 key pillars for future research to bring this concept into standardized clinical environments. We will first run multiple subject clinical trials to measure patients' comfort. We will monitor localized skin pressure thresholds, thermal sweat accumulation within the 2 mm liner gap, and long-term ergonomic comfort in different demographic groups. Second, we establish an open-source anatomical database of non-severed lower arm meshes. This library will provide the foundation for a base set of structural templates to drive automated algorithmic scaling and fitting workflows to accelerate the CAD stage. The third is the standardized physical testing. We will subject physical FDM printed PLA prototypes to destructive tensile, torsional, and cyclic fatigue testing in a physical laboratory setting. This empirical testing will directly validate our finite element simulations and prove our calculated safety factors work under real-world failure conditions. Before I end this presentation, I would like to thank the institution's funding that made this research possible. This research was funded by the 3D Care Project, Sustainable Orthopedic Solutions with AI-driven design, and 3D printing for patient-specific care. I would also like to note that the opinions and views expressed in this presentation are strictly those of the authors and do not necessarily reflect those of the European Union or the European Commission. In summary, our study establishes an end-to-end digital to physical pipeline that combines standard smartphones with advanced topology optimization to produce custom, lightweight, and low-cost prostheses. We believe this framework can serve as an accessible blueprint for next-generation decentralized healthcare. Thank you very much for your time, your focus, and your attention. I will now conclude my presentation and open the floor for any questions or comments you may have.